I am going to do, so, okay, so here's some explanation. So I just got done describing the VSEPR theory, valence shell electron pair repulsion. And the basic idea is that your atoms that are bonded in lone pairs are going to get as far away from each other as they possibly can. They're going to repel each other. If I have two atoms, like this molecule here, so if you hit, make this, hit reset, add just two atoms, doesn't matter if they're single, double, or triple bonds. I'm just going to go with single bonds. No matter what I do to this, if I move this quickly, I can make it bent. I can bend them so that they're not 180 degrees away from each other, but they eventually go back. And the reason why is because if I bend them and they get closer together, that means the repulsions have increased. This arrangement is the furthest away those bonds can get from each other. And that minimizes the amount of repulsion between those atoms, or sorry, the electrons that are in the bond. We're minimizing the valence shell electrons repulsions. That's why I was shortened, because it takes a long time to say that versus VSEPR, right? Now, I'm going to go ahead and show the bond angles. So you can see on this that it's showing that it's representing that we've got 180 degrees between those two bonds. Now, I don't know how much geometry you guys have been taught in the past, but I know it's not a lot if you're not in geometry, but it should be in, the only geometry I'm talking about today should be pretty basic. I think it's enough that you have covered it already at some point. So if you watch carefully, or if you do this on your own, if you try to bend this thing and make them closer, so yeah, you're going to successfully make that angle smaller, but it always goes back to 180. That's due to that repulsion. Now that's only two atoms attached to the central atom. If I add another bond, I change my angles. Because what we've done is we've added another set of electrons, another set of electrons, another high electron dense area that's going to start competing with and repelling the others. Now, it's three-dimensional in structure, but pretty flat, so almost two-dimensional. Because if I get it like this, you can see these are all on the same plane. Okay. But they're 120 degrees away from each other because that is the furthest away, or that's the closest they can get, and reduce the repulsions. Or I guess you can say they're the furthest away they can get with reduced repulsions. Because if I try to rotate this upwards, okay, so if I make this go up, I may make this angle between the two atoms shorter, smaller, get them closer together, and increase the angle between these two. But if I increase this angle, I'm going to increase the repulsions over here. Well, you think, well, Mr. K, pull it down. Okay. If I try to pull this down, I'm going to make all of the angles closer. So this is the 120 degrees. That is the least repulsions that are going to occur between the atoms. Is you have any luck getting in? Okay. I just sent her an email with the link. Have her try that. All right. Now, what happens if let's slap a lone pair on there? Well, I'm going to take off one of those single bonds, go back to the 180 degrees, and if I put a lone pair on there, so it's not a bond, I essentially get the same thing. Now, they don't, on this, in this diagram thing, they don't show the angle between the lone pair and the bonds, but it would be 120 degrees. There, there, good enough. So this is what we're talking about with the high electron dense areas. Let's talk about earlier when I talked about the molecular structure. The structure just depends on what the electron groups. It doesn't depend what they are. They're all going to repel each other, and we're going to treat them as if they were the same. Now, full disclosure, if I had a lone pair of electrons versus a bond, technically, this angle would be a little bit different. Lone pairs of electrons don't repel the same way as bonded electrons. There is a little bit of difference. We're not going to worry about that difference. Okay. Now, here's where we get to a more three-dimensional structure. It's where, I hate to say it, lose some people in terms of the understanding and be able to visualize it. This model is the digital models that you're making here, they're really good. Okay. Tell her to watch the videos. She'll be all right. So one of the things is that you know yourselves pretty well. Can you visualize in your head three-dimensionally? And some people can, some people can't, some people are ill, sometimes depends on how complex the thing is. So to help you guys out that are here, and for those of you who are at home, I'm going to have them on, next week as well. I've got models of all the different shapes that you guys are going to encounter. Physical. Because it does help to come up and hold one, say, okay, this that I have in my hand is the same as what's in that diagram. I'm going to switch to my camera here for you guys at home. So, share. One, three. So that model I had drawn is this. I know it's a little blurry, but, and I know even on screen it's a little bit different, but if I hold it like this, you can see it's got three-dimensional structure to it. Whoa, here we go. This we would call a tetrahedral. Why? Because it's got four sides. 1, 2, 3, and then the base 4. That's the shape. Okay. Let's switch back to the program. So again, I'm going to switch one of these out for a lone pair and see that we still have that same basic structure. Okay. Now, this is where we get a distinction between our molecular and group geometry. So down in the bottom left, I'm going to turn on the electron and molecular geometry so we can see what those are. And we can see that they're different. In this molecule, I've got 4 high electron dense areas. They're all going to be 109.5 degrees away from each other. The basic structure is what we call a tetrahedral. But I'm going to take off, I'm not going to take off, I'm going to not show the lone pairs. So I just turned that off. So our molecular geometry is based only on these atoms on the screen. And that shape is a little different than that shape. That's why they have 2 different names. If I take that lone pair off and add a bond, you'll see here that the electron group geometry and the molecular geometry are the same. Because remember, the molecular geometry is basically describing the shape based on atoms bonded. And I have 4 atoms bonded. I got 4 high electron dense areas. Electron group geometry is based on anything, bond and lone pair. Well, they're 4 bonds. They're going to be the same name because they have the same structure based on what they're counting. But again, if I take off that singly bonded atom and put a lone pair, my name changes because molecular geometry only takes into consideration bonded atoms. Crying out loud, get back up there. There we go. And that lone pair is not a bonded atom. Questions? Okay. So in Canvas, you got a link to the VSEPR theory activity. Go ahead and open that up. Now, I know that I have a couple of people from Mr. Milligan's class. And we found out, dawned on me last period that Mr. Milligan had you guys do the Lewis structures for about, I think it was like 24 molecules or something like that in that assignment he gave you last week. I think it was last week. Yeah, last week. And then I gave you the Lewis structure 2 document. So in part A here, it says you're going to draw Lewis structures or redraw the Lewis structures for each of the compounds in the table. Refer to the number since you already have most of the Lewis structures done. So down here in the table, I've got the compound, and then I've got the letter that corresponds, is it Lewis structure document 1 or Lewis structure document 2? And then the number next to it to tell you which one it is, so you don't have to go searching everywhere for it. So you have the Lewis structures done for the majority of these. Now, Mr. Milligan students, for example, your document that you had, the first document, I know you did not have silicon disulfide, the very first one on here. So if you don't have that compound, you're going to have to start from scratch with it. I don't think there's that many of them, but there are a few. Okay. So most of these you have already. A couple of them are new, and they say new. So you're going to have to draw your own Lewis structures from scratch for those. Oh, you know what? Okay, I need to do this real quick. Let's see. Format, text, nope, not superscript. So this compound, and there's a couple of others, if you keep scrolling down, would actually have multiple central atoms. So when you're doing these, you're going to include or a VSEPR notation, shape, all that stuff for each atom that could be considered essential. When you get to the point where you're doing those, I can help you out with that. Now, you're going to use the pHET site where we're making the models. And you're going to make the models based on your Lewis structure, make sure the number of bonds is correct, make sure the lone pairs are correct, and use the information that you are given to be able to answer the other parts. So you're going to have your Lewis structure. You're going to put your VSEPR notation and steric number here. You're going to use the pHET site to determine your group and molecular geometries. That's where you're going to go through and you're going to look at down here in the bottom left. Okay, my molecule geometry is trigonal pyramid. My electron geometry is tetrahedral. That's the things that you would fill in here. I call it group geometry. The program called it electron geometry. Remember, 3 different names for the same thing. And last, you're going to, well, not last, you're going to fill in the bond angle while I'm here. You're going to leave polarity blank for now. This is something we'll either begin on Wednesday. And if I don't on Wednesday, it's like, I'd probably give you guys like a 15, 20-minute thing to do. It's not going to be anything big if I have time to set it up. If not, then we'll just start in on class on Thursday. Okay. So you're not going to be filling in this last column with polarity right now. The last thing that you're going to do is you're going to include the bond polarity for each bond. So every bond, you're going to represent polarity somehow. Now I'm going to show you how to do that. If you scroll to the very last page in that document, you're going to see that I've got the electronegativity values that you learned about yesterday. And we're going to use those to determine the bond polarity. So if you were to look at that table, you would find that oxygen has an electronegativity of 3.5. I only know that because I use it so often. Hydrogen has an electronegativity of 2.2, both of them. Ethan, I know you got a sibling, right? I know you got an older sister. Is that it? You got a younger, oh, you're a middle, you're a, oh, you got an older sister and a younger sister? Oh, I'm sorry, man. You okay? So if mom and dad gave you 3 one cupcake and told you to share, who gets the most? Be honest. Oh, no. Your older sister let you have more? Yeah, I'm the only boy. You tell your sister, Mr. K says she's not doing her job right. Okay. The true nature of it is the oldest should always get more, right? I got a little brother. I didn't give him equal amounts. No way. I I gave him enough to where he wouldn't go rat me out. So that's what your sister should do. So if we got a cupcake, I'm going to cut it in 60-40. If he whines about it too much, maybe I'll give him like 45-55, and I get the 55 because he was dumb and he couldn't do math right. Okay, so same basic idea here. We've got electrons that are being shared, but they're not being shared equally. Oxygen is like the big brother or big sister. It's got a larger value. It's going to get a larger share. It's going to attract the electrons more strongly. So to represent that, the electrons are going to be attracted to the oxygen more strongly. We put an arrow on the bonds to represent that those electrons are going to shift to be closer to the oxygen. Now, next time we're going to talk about polarity of the molecule. Yesterday, you learned about the polarity of the bond, where we have an imbalance in charge here. And what that does is that makes this end of the bond with oxygen slightly negative. And that makes the hydrogen here slightly positive. What do opposites do to each other? What do opposites do to each other? They attract. So if I had another water molecule and my oxygen's negative and the hydrogens are positive, could we get those two water molecules to attract each other? Absolutely. That's why your water is liquid at room temperature. That's the polarity of the molecule. We'll talk about that next time, okay? Or maybe like I said, maybe Wednesday. So in preparation for that, on your Lewis structures, I want you to draw the arrows to represent the polarity of the bonds. Okay? Draw Lewis structures. When you're drawing them, I think in the instructions, so try to draw them so that they represent the three-dimensionality that the molecule actually has. You don't have to be a perfect artist and draw it like it is on the screen. Still use letters and lines and stuff, but like this is water. It's got a bent structure. Don't draw it in a straight line. That's misleading. Okay. So you're going to draw them, put the arrows on the lines. You're going to determine the VSEPR notation and the steric number. All of those, with the exception of the arrows, all those things you've got done already. You came in today with the VSEPR notation and the steric numbers. On Lewis structures, you already had done. Okay. Make them on the model kit, on the digital model, and then fill in what the molecular shapes are and angles. Quick note. If I had a compound like this, this does not have a single central atom. It's got what we would consider to be multiple central atoms. So I would kind of designate this carbon 1 and this carbon 2, all right? And what we would do is we would then look at and say, okay, I want to know the geometry around this carbon. So we would look at that. We look at this carbon, and these two hydrogens. And this would be our central atom. We do our VSEPR notation and stuff for that carbon. Follow me on that? And then we would do another one. We'd look at what is it for this carbon, and we treat that carbon as a central atom. That's why in the grid, you'll see some that have C1, C2, oxygen 1, or just like a separate oxygen, because you may have multiple central atoms. Questions about that? Okay. So go ahead and get started. Those of you at home, you're more than welcome to stick around. I will leave the Zoom session on. So if you've got questions, you can ask. I can come up to the board and help explain things to you if need be. If you think you're good, then you're welcome to go, because the rest of the time I'm going to give for work. Okay? There's no excuse for not coming into class next time with these things done, because you're going to have almost about 50 minutes to get these done. And you're going to get a majority of them done. Okay? Questions? Okay. Get started. Stop this. Oh, don't forget, you guys here, come up and see me if you want. I strongly encourage you. The funky looking thing, that's going to represent the lone pair.